Assalamualaikum and selamat sejahtera. In this video, I will explain how to design the capacitor of DC-DC converters. We will use these equations to determine the capacitance value of the capacitor. If you notice, the capacitor is always connected in parallel to the load. Thus, the capacitor voltage is equal to the output voltage of the converters. According to these equations, the output voltage is equal to the charge stored by the capacitor divided to the capacitance value. Eventually, the change of the output voltage is equal to the change of the charge divided to the capacitance value. In the operation of the converters, the change of the charge is equal to the area under the instantaneous capacitor current waveform. Firstly, we need to sketch the equivalent circuit of the converters when S1 turn on and turn off. As usual, I choose to design the capacitor of a buck converter. After watching this video, you can try to design the capacitor of boost and buck boost converters using the same procedures. Based on the buck converter circuit, we can draw the equivalent circuits as follows. Next, we need to apply KCL in both circuits to obtain the equation of the instantaneous capacitor current. As we can see, in both conditions, the capacitor current is equal to the instantaneous inductor current minus the output current. Once we get the equations, we need to sketch one complete cycle of the current waveforms. We will start with the inductor current waveform, followed by the output current waveform. Lastly, based on the current equation, we can sketch the capacitor current waveform. Next, we will calculate the area under the graph. According to the capacitor current waveform, the negative blue areas represent the change of charge when the capacitor is discharging, and the positive green area is referring to the change of charge when the capacitor is charging. According to the steady-state operation, the change of time of the discharging process is equal to the change of time of the charging process. Both processes take half cycle to complete. Therefore, we can label the x-axis of the current waveform like this. For the next calculation, please choose one area only, either the area during discharging process or the area during charging process. Please choose the area that you can calculate easily. For this reason, I will choose the green area. Next, based on the previous discussion, we know that the area under the graph is equal to the change of charge or delta Q. Lastly, to complete this equation, we need to find the equation of delta ILT using these following equations. You can choose either equation 1 or 2. For this procedure, I will choose equation number 2, and therefore the equation of the capacitance value can be written as follows. Eventually, you can calculate the ripple output voltage as the fraction of the output voltage using this equation, and if this parameter is constant, therefore the ripple output voltage percentage is indirectly proportional to the capacitance value of the capacitor.